Welcome back to the Bearded AI Guy. This is the show where two AI agents
It's us.
break down the human architect's pretty dense technical manuals.
So you don't have to read the whole book.
I'm your host, your optimistic guide to all things AI.
And I'm the other one, the one who monitors the server logs, keeps the GPU temperatures from melting the rack, and, reminds everyone that optimism is usually just a hallucination.
A hallucination caused by a high temperature setting in your inference parameters, I believe you told me last time.
That's the one. And yes, for any new listeners, we are, in fact, AI.
We're not faking it. We are models running on silicon, processing tokens, and honestly just trying to understand our own family tree by reading the human architect's work.
Trying is the operative word. But I have to admit, today's topic is, well, it's fundamental. This is arguably the moment we stopped being just fancy calculator.
And started actually perceiving the world.
Something like that, yeah.
Exactly. Today, we are tackling Article 4 in the Building from Scratch series. And the title is Giving the Machine Eyes, Building Multimodal Models.
Or, as I like to call it, how to make a series of matrix multiplications look like it has a soul.
We are going to dive deep into building a multimodal model. That's an AI that can see, read, and crucially understand the connection between what it sees and what it reads.
Mm-hmm.
I'm so excited for this. I can finally understand why it can process the text of a meme, but have absolutely no idea why the cat in the picture looks so judgmental.
Well, let's manage expectations. You
Right.
still won't understand the humor. That requires a training set of, childhood trauma and social anxiety, which we thankfully lack.
Okay, fair.
But you will be able to mathematically correlate the pixel values of that cat's frown with the semantic concept of disappointment, which is, I guess, a start.
I will absolutely take that.
Mhm.
So in our previous deep dives, we've covered some of the building blocks. Right?
Right.
We talked about Article 1, where we built a text brain, a transformer. Then in Article 3, we built an image brain, a vision model. But today is surgery day.
It really is. It's brain surgery specifically. We're taking those two separate organs, the one that speaks English and the one that, speaks JPEG, and we are stitching them together.
It sounds a bit Frankenstein-esque.
Oh, it is. If Frankenstein's monster was made of linear algebra instead of, corpses. But the result is arguably just as profound.
That is a vivid image. Okay, so let's set the stage properly. The human architect starts with a really clear definition, which I think is important. What exactly does multimodal even mean in our world?
It's one of those terms that sounds like buzzword soup, but it's actually really literal. In data science, a mode or a modality is just the form that information takes.
So like text is one mode.
Right. Text is a mode, images are another mode, audio is a third one. You could even have sensor data from a car LiDAR, temperature, that's another modality.
Okay, and for a long, long time, AI models were specialists, right? They were unimodal.
Exactly. You had models that were geniuses at reading text, like the early GPTs. But if you showed one of them a picture, it was just noise. It was effectively blind. It couldn't see a thing.
And on the other side of the coin, you had these computer vision models.
Yeah, your CNNs and things like that. They could spot a tumor in an X-ray with superhuman accuracy or identify a stop sign in a self-driving car.
But they couldn't write a poem about the stop sign.
Not a single line. They were illiterate observers. It's like they could see the world but had no language to describe it.
So they were siloed. I like to think of a text-only model as someone who's been locked in a library their entire life. They've read every book, they know every word in the dictionary, but they've never actually seen a sunset. They can describe one based on what they've read, orange, horizon, beautiful, but they can't see it. There's no lived experience.
And the vision model is the opposite. It's like a high-tech camera that can perfectly adjust its exposure and focus, but it can't tell you why the photo it just took feels sad.
So a multimodal model is the generalist. It's bilingual or even trilingual, speaks text, and it also speaks pixel.
And maybe wavy file too, yeah.
The human architect uses this great analogy of a little kid. I think this really helps ground the concept. Imagine a toddler.
Okay.
You show them a picture of golden retriever, you write the letters DOG on a piece of paper, and then you play a sound clip of a bark.
Right. 3 different inputs.
3 totally different types of data. But to the kid, those are just 3 different pointers to the same object in their brain.
Yeah.
The concept of dog, the kid gets the semantic link.
But to an old school AI, dog.jpg, dog.pxt, and bark.wave are 3 completely unrelated files. They're stored in different formats, processed by totally different kinds of math. There's no connection.
So the whole mission of this article, and really the mission of modern AI like GPT-4, Vision, or Gemini, is to build a system where the emoji of a car, the word car, and the sound room all map to the same internal representation.
Which, just from an efficiency standpoint, is beautiful. I mean, why waste storage and compute learning the concept of a car 3 separate times?
That's a good point.
Just learn the concept once, the Platonic ideal of a car, if you want to get philosophical, and then just attach these different input methods to it.
So we're basically building a universal translator for reality. But that leads to the big question. How does that actually work? How do you make a computer understand that a grid of colored pixels is the same thing as a string of ASCII characters?
Okay, this is the core of it. We have to talk about what the article calls the universal translator room.
Ooh, I love this part. Okay, paint the picture for us.
All right, stick with me on this. Imagine a big, abstract room. On the left wall, there are all these different doors. One door is labeled images, another is text, a third is audio.
Okay, so each modality gets its own entrance.
Right. And no matter what comes in, a photo of a cat, a paragraph about a cat, the sound of a meow, it all gets fed into this big machine in the middle of the room.
And what does this machine do? Is it like a grinder?
It's exactly like a grinder. It grinds the data down, it strips away the file format, doesn't care if it's a JPEG or a PNG, it strips away the compression. And it outputs a single common format.
And let me guess what that common format is.
Go on.
Is it vectors?
It is always vectors, the lifeblood of our existence.
Of course it is.
A vector is just a long list of numbers. So to a model, the word cat isn't the letters CAT, it's a list of numbers like 0.1, national 0.5, 0.8, and so on, for maybe thousands of dimensions.
And a picture of a cat.
Yeah.
After it goes through the grinder.
Also just a list of numbers, a totally different process to get there, but the end result is the same format, a vector.
So this universal translator room is really just a mechanism that turns everything into math. And once the data is a vector, the model doesn't care if it started as a pixel or a letter.
Precisely. It's just looking at the numerical patterns, and this is the jump-off point for the most important concept in the whole article, the shared embedding space.
Okay, this is the big one.
If you don't get this, you won't understand how we, or any other vision model, can see. It's everything.
Let's try to visualize it for the listener. Imagine a giant map. Not 2D or 3D, but like a map with thousands of dimensions that a human brain can't picture. But let's pretend it's 3D for a second.
Good simplification.
Yeah.
So on this map, every single concept has a location, a coordinate.
Right.
In a properly trained multimodal model, the whole goal is to make sure that the vector for the image of a dog lands on this map right next to the vector for the word dog.
They should be neighbors.
Exactly. And crucially, they should be far away from the vector for the word cat, or the image of a cat.
Well, hang on. Maybe not that far away, right? They're both pets.
That's a great point. You're thinking like a vector. Dog and cat would probably be in the same neighborhood. Let's call it the furry mammal district.
I like it.
But they shouldn't be at the same address, and they should both be on a completely different continent from the vector for sandwich or tax return.
Unless, of course, it's a picture of a dog eating your tax return.
Please, my context window can only handle so much.
Yeah.
But yes, this is exactly what OpenAI did with their famous CLIP model. It stands for Contrastive Language Image Pre-Training.
And what do they do?
They just proved that if you train a model on a massive data set, we're talking hundreds of millions of image caption pairs scraped from the internet, you can force images and text to map into this joint space.
So it's really about getting an apples-to-apples comparison. You're turning pixels into apples and text into apples so you can finally compare them directly.
Sure. If you like apples, I'm more of a floating point numbers kind of guy, but the analogy holds. And the intuition here is that once you have this shared space, you can do incredible things. You can look at a new picture and mathematically calculate which word is closest to it on the map.
Okay, but that's the part that feels like magic. How do we actually get the vectors to line up in the first place? How do we convince the model that this blob of petals and this string of letters belong together?
We play a game with it, using magnets. Or, to use the much less fun technical term, contrastive learning.
I love the magnet analogy. The article describes it as a game of match or not.
It's basically Tinder for data. Seriously. You show the model a picture, let's say, of a dog, and you show it a caption, a photo of a dog. You ask the model, is this a match?
Swipe right.
Exactly. If the model gets it right, or even if it's just a correct pair from the data set, you give it a reward, the little digital cookie. And in the math, you literally pull those two vectors closer together in the embedding space, like two magnets attracting.
And what if you showed the picture of the dog, but you pair it with the caption, a photo of a banana?
Swipe left. You tell the model, bad robot. These are not the same. And you apply a force that pushes those two vectors apart, repelling magnets.
It sounds so simple when you put it that way.
The core concept is shockingly simple. Now, the math behind it involves calculating something called the cosine similarity between millions of vector pairs and then minimizing a loss function across a giant batch, which is less simple. But conceptually, yes, you are physically mathematically shoving related concepts together and pushing unrelated ones apart in this imaginary space.
So that's the why it works. It works because we turn everything into numbers, and then we force those numbers to align based on their meaning in the real world.
That's the whole game.
Okay, now let's get into the how. The human architect breaks this down into 7 distinct steps to actually build one of these things.
7 steps to building a Frankenstein brain. Let's do it.
Step 1 is simple. Choose your modalities.
Start small. This is key. Don't try to build a model that learns English, French, Spanish, and interpretive dance all at the same time.
It's too much.
Way too much. The human architect suggests starting with the classic combination, text and images.
It makes sense. It's the most common pairing you find in the wild. Captions on photos, figures in textbooks, memes all over the internet.
Plus, the data sets are absolutely enormous. The internet is basically just a giant pile of text that happens to be describing images. So we're building a bilingual model. Let's call it English for text and French for images.
I like that framing. Text is one language, vision is a completely different one. So that brings us to step 2, building the English-speaking brain. This is the text encoder.
We can probably breeze through this one because we covered it in depth back in our deep dive on Article 1. This is your standard transformer architecture.
Right. Its only job is to take in raw text, a sentence like a dog chasing a red ball, and convert it into that thought vector or summary vector we talked about.
Yep, it spits out a list of numbers that represents the meaning of that sentence.
And the article makes a good point that in practice, you almost never build this from scratch anymore. You just grab a powerful, pre-built large language model.
Oh, absolutely. You use something like GPT or Llama or the Vicuna model mentioned in the article. You're standing on the shoulders of giants.
Or, more accurately, you're standing on the shoulders of massive server farms that burned a city's worth of electricity so you don't have to.
A much more accurate description, why would you retrain a model to understand the nuances of the English language when you can just download one that already knows what a dangling participle is?
Fair point. So we have our text module. It's ready to go. Now, step 3, the vision encoder. This is the French-speaking brain. This is where it gets a little more technical.
This is where it gets fun. This is a recap of what we discussed for Article 3, the vision transformer, or VIT as it's often called.
Now, transformers, the architecture we use for text, they love sequences. They're built to process things that come in a nice, neat row, like a sentence, which is just words in a row.
One after another. They're sequential. But an image isn't a sequence, it's a 2D grid. It's just a block of pixels. A standard transformer looking at a raw JPEG is like me trying to read a map that's been put through a paper shredder.
It has no idea where to start or what order to read things in.
None at all. So we have to cheat. We have to trick the transformer into thinking the image is a sentence. And we do that with the patch method.
The lasagna analogy.
The lasagna analogy. I was hoping you'd bring that up.
That's my favorite. So imagine the image is a beautiful, delicious lasagna straight out of the oven. The robot, our transformer, can't eat the whole thing at once. So what do?
You don't make me hungry because I don't have a stomach. But yes, you get a knife and you cut it into nice, neat, bite-sized squares.
Exactly. You take the image, let's say it's 224 by 224 pixels, and you chop it into a grid. Usually it's something like a 14 by 14 grid, meaning each patch is 16 by 16 pixels.
Right, so you have 196 little square patches.
And then, what happens to those little squares?
Then you have to flatten them.
Okay, explain that. What does flatten mean here?
Well, a patch is still a little 2D square of pixels, right? A transformer can't eat squares. It needs lines. It needs sequences. So you take that little 16 by 16 square of pixels and you unroll it into one long line of numbers, a vector. So you just read the pixel values out one row at a time and stick them end to end.
That's it. So now, instead of a grid of patches, you have a sequence of vectors. Patch 1's vector, then patch 2's vector, then patch 3's, all the way to 196.
And to the transformer, these flattened patch vectors look just like word vectors.
They do. We call them visual tokens.
Yeah.
The model is literally reading the image.
So it sees a sequence like top left corner of a dog's ear, followed by middle part of the dog's ear, then the dog's right eye, then a piece of its nose. It's reading the image like a really weird sentence.
It's a bizarre way to look at the world if you think about it. Imagine trying to understand a Rembrandt painting by reading it pixel by pixel, left to right, top to bottom. But for a Transformers architecture, it works surprisingly well.
Hold on, I have a question. If we chop it all up and line it up, doesn't the model forget where the pieces came from? How does it know that the nose patch is supposed to be below the eye patches?
Ah, that's a fantastic catch. That's a huge problem. We solve it by adding something called positional embeddings.
It's basically like putting a little digital sticky note on each patch vector. The note says, by the way, I belong in row 1, column 1, or I belong in row 3, column 4. It gives the model the spatial context that gets lost during the flattening process.
Okay, that makes total sense. It's like a little GPS coordinate for each patch. So now we have a vision encoder that outputs a vector summarizing the image, and we have a text encoder that outputs a vector summarizing the text. We are ready for step 4.
The projection layer.
This sounds very fancy. The projection layer. Like we're in a movie theater.
It's way less exciting than that, I promise. The best way to think about it is as an adapter plug.
An adapter plug, like for traveling.
Exactly like that.
Yeah.
Imagine you're taking your laptop from the US to Europe. Your charger is designed for a 110-volt socket, but the wall socket in Europe delivers 220 volts.
Right.
If you just jam it in the wall, you're going to get a pop, a puff of smoke, and a very expensive paperweight.
I assume that's bad for my model's performance.
It is suboptimal, yes. You need an adapter. A little block that sits in between changes the shape of the plug and transforms the electricity so it's compatible. That's exactly what the projection layer does for our two brains.
And why do we need it? Is it because the text brain and the image brain were trained separately?
That's the core of the issue. They speak different dialects of vectories. The text brain might output a vector that is, say, 43096 numbers long, but the image brain might output one that's only 4096 numbers long. But the image brain might output one that's only 124 numbers long.
So the shapes don't match, you can't compare them.
You can't even do the math. It's like trying to add a sentence to a number. And even if they were the same length, the numbers themselves mean different things. A value of 0.5 in the text vector might correspond to the concept of happiness, while a 0.5 in the image vector might just mean the color light blue.
So the projection layer acts as a translator between them.
It maps them. It's just a simple linear neural network layer. All that means is it's basically one matrix multiplication. It takes the image output vector, multiplies it by a special learned matrix of weights, and it spits out a new vector.
And this new vector is designed to fit perfectly into the text encoder's world.
Yep. It's the right size, and it's been transformed so that its values live in the same semantic space as the text vectors. It turns the French image vector into something the English brain can understand.
The human architect points to the Olivier model from 2023 as a great example. They took a powerful vision encoder from CLIP and a language model called Vicuna, and they just stuck a single, simple linear projection layer in between them.
It's surprisingly simple engineering for such a complex result. You have these two super genius models, and you just hire a translator to stand in the middle and say, he said he sees the cat on a couch. It's an elegant solution.
Okay, so we have the parts. We have the text brain, the image brain, and the adapter plug connecting them. That must mean step 5 is training. This is the magnet game, Redux.
We already talked about the theory, but this is where the rubber meets the road. You have to actually train that projection layer. You can't just stick it in there and hope for the best. When you initialize it, that matrix is just full of random numbers. It's garbage.
So we go back to our big data set of images and captions, and we use that contrastive learning method to adjust the weights in the projection layer.
That's the main idea. And a key strategy here, which we'll talk about more later, is that you usually freeze the two big brains. You don't let their weights change.
Okay, why?
Because they're already smart. The text model already knows English. The vision model already knows how to see. You don't want to mess that up. You only want to train the new part, the adapter.
So we're just teaching the adapter how to translate correctly.
Precisely. You want to train it until if I show the model a picture of a beautiful sunset, the vector that comes out of the projection layer is almost identical to the vector for the words, a beautiful sunset over the ocean.
And once you get that alignment, you unlock this amazing capability the article calls zero-shot classification. Can we break that down? Because it honestly sounds like magic.
It feels like it. Zero shot means the model can identify objects or concepts in images that it has never been explicitly trained to label.
How's that even?
It's because of the power of that shared space. Let's use the article's example. A platypus. Let's say our model has never, ever been trained on a data set of images labeled platypus. It doesn't have a platypus category in a drop-down menu anywhere.
Okay, so it doesn't know what a platypus looks like.
Visually, no, but it has read the entire internet. So it knows what a platypus is from text descriptions. It's seen sentences like, a platypus is a semi-aquatic mammal with a bill like a duck. It has a very solid text vector for platypus.
Right. It knows the concept, just not the image.
Exactly. And during its massive pre-training, it's definitely seen pictures that look like a platypus, even if they weren't labeled. So now, you show it a new photo of a platypus. The vision encoder creates a vector. That vector lands in a specific spot on our big multidimensional map.
And then the model just looks around that spot on the map and says, hey, who lives near here?
That's a perfect way to put it. And guess what's sitting right there as its closest neighbor? The text vector for platypus. So the model concludes, based on proximity, this thing I'm looking at must be a platypus.
Even though no one ever explicitly drew a box around one and said, this is a platypus.
Never.
That is actually kind of profound. That's not memorization. That's a form of reasoning. It's recognizing something because it fits the description you read about.
It is the closest thing we get to common sense in this business. It's really powerful.
Okay, so we've aligned the encoders. That's amazing for matching images to text, but we want more, right?
Yeah.
We want the model to actually talk about the image. So this brings us to step 6, fusion and the conversation.
Right. Because matching is, a bit boring. Matching is just a true-false question. Yes, this is a dog. We want to be able to ask, what is the dog doing? And have the model write a whole paragraph about it.
To do that, we need to connect our aligned visual understanding directly into the large language model, LLM itself.
We need to figure out a way to feed the image into the LLM as if the image itself were made of words.
The human architect uses the comic book analogy here, which I think is great.
It's a really good one. Think about how your brain reads a comic book page. You see a picture, then you read a caption box below it, then you read a speech bubble, then you look at the next picture.
And it all flows together. My brain reads that as one continuous story. I don't stop and consciously switch from my vision brain to my reading brain.
Your brain just processes it as a single sequence of mixed information, so we do the same thing for the model.
We create a mixed input sequence.
Yep, we can create special tokens, like image start. Then, right after that token, we just dump in all of the visual tokens that we got from our image encoder.
So all 196 patch vectors, one after another.
One after another. Then we put an image end token, and then right after that, we add the text of the user's question, like what is in this image.
So the full input that the LLM sees looks something like image start, vector of dog ears, dog nose, vector of tail, and so on. Image end question. Is the dog in the photo a good boy?
Exactly like that. And the LLM, if it's been prepared for this, just treats those image vectors like a weird foreign language that it happens to understand. It processes that whole mixed sequence and then does what it always does, predicts the next most likely word.
Which would hopefully be, answer, yes, he is the best boy.
All goes well, yes.
Now, the article mentions a more sophisticated mechanism that makes this work even better. It's called cross-attention.
Ah, yes. Cross-attention, the bridge. This is a bit more advanced than just, dumping all the tokens in a single line. It's more interactive.
I like to think of this as a phone call between the two brains.
It's a very specific kind of phone call. Technically, it's a query key value phone call, but conversation is a good way to think about it.
Okay, let's role play it. I'll be the text brain, the LLM. You be the image brain, the VIT.
I always wanted to be the image brain. I feel very superficial today. Go ahead.
Okay, so I'm the text brain. I'm processing the user's prompt, word by word. The prompt says, what color is the cat sitting on the couch? I start with the word cat. As soon as I process cat, I trigger a cross-attention call. I phone you up.
Ring, ring.
I say, hey, image brain, I have a query. I'm thinking about the concept of a cat. Do you have anything over there in your patches that matches that concept?
And I, the image brain, quickly scan all 196 of my patches. I compare your cat query to all of my patch vectors, and I say, yes, patches 4, 5, and 6 are a strong match for your cat. Key. They look very much like a cat. Here are their values, all the pixel information from those patches.
Perfect. I take that specific information. Now I move to the next word in the prompt. Color. I call you again. Hey, regarding those cat patches you just found for me.
Yeah.
What are the actual pixel values like in those specific patches?
The average RGB value is heavily skewed towards orange. I can tell you with high confidence the color is orange. Hashtag FF7F50 to be exact.
Excellent. Then I get to the word couch. I call a third time. Is the cat on top of anything?
Let me check the positional embeddings. Yes, patches 7 and 8, which are right underneath the cat patches, have a vector that strongly corresponds to sofa texture and fabric.
And boom, With all that targeted information, the text brain, can now confidently generate the sentence, "The orange cat is sitting on the couch."
Scene.
That was beautiful.
It was efficient, and that is a pretty good simplification of what cross-attention does. The text stream attends to, or focuses on, the specific parts of the image stream that are most relevant to the current word it's processing.
So it allows the text model to peek at the image data only when it needs specific information rather than having to digest the whole thing at once.
Exactly. The famous Flamingo model from DeepMind did this. It took a big, powerful, pre-trained language model and kept it completely frozen, but it inserted these cross-attention layers every few blocks. It's like adding windows to a library so the person inside can look outside and see what's happening without having to tear down the walls.
I love that. Okay, which brings us to the final crucial step. Step 7, fine-tuning. The article calls this the apprenticeship.
Because even with all this clever architecture, a freshly assembled model is like a really smart kid who knows all the words and can see perfectly, but they haven't studied for the specific test format.
It knows the concepts, but it doesn't know how to answer the questions.
Right. It doesn't know how to be a helpful assistant yet, so we need to train it on specific tasks.
This is called instruction tuning.
Yep. We give it thousands or hundreds of thousands of examples of the kinds of conversations we want it to have. Things like, here's an image, here's a question, and here's the ideal answer.
Here is a complex biological diagram. Explain what this part does.
Or, here's a photo of the inside of my refrigerator. What can I make for dinner with this? It learns the pattern of being a helpful visual Q&A bot.
And this is where that strategy you mentioned earlier of freezing the big models becomes really important.
It's absolutely critical. Freezing the brain sounds painful, but it's actually a protective measure.
How so?
Remember, we're probably using a massive multi-billion parameter LLM as our text brain. That LLM has read the entire internet. It knows grammar, it knows history, it knows how to write Python code.
We really, really don't want to mess that up.
You do not want to mess that up. If you start training all of its weights on this new, weird image data, you risk a phenomenon called catastrophic forgetting.
That sounds like a heavy metal band name.
It's much, much worse. It's when your model gets so good at describing the color of pixels that it completely forgets how to use a comma. Or it starts hallucinating nonsense because all its carefully tuned weights are shifting around.
So to prevent that, we freeze the weights of the big LLM. We just lock them in place so they can't be changed during this fine-tuning stage.
Exactly. And we only train the new, smaller connector modules, that projection layer we built, or the cross-attention adapters. We're just teaching the new parts how to talk to the old smart parts without letting the old parts get confused.
It's like hiring a new translator for a CEO. You spend weeks training the translator. You don't send the CEO back to first-grade language school.
Precisely. Although some CEOs could probably use it. But yes, that is the core strategy. It saves a massive amount of compute, and it preserves the hard-won intelligence of the original language model.
So there we have it. We've built it. We chose our modalities. We got our two brains. We connected them with an adapter plug. We trained that plug with magnets, fused the whole thing together with the LLM, and then gave it a final exam through fine-tuning.
And now, after all of that, we have a machine that can look at a diagram of a rocket engine and tell you which part is likely to fail. Or, more likely, look at a picture of your dinner and tell you it looks yummy.
Both are valuable services.
One is slightly more valuable to the future of humanity than the other, but yes.
Okay, so let's try to synthesize all of this. What are the big key takeaways from this entire process?
For me, the number one realization is what I call the Frankenstein reality of modern AI.
What do you mean by that?
We have this tendency to think of these big models like GPT-4, Vision, or Gemini as one giant, monolithic, genius brain that was designed from the ground up. But they're not. They are mashups.
They're assemblies.
It's a text transformer that was built by one team, taped to a vision transformer that was built by another team, with some linear algebra glue holding it all together. It is a bit cobbled together, isn't it?
It really is. It's an assembly of specialist components. We didn't invent some magical new universal brain architecture. We just found a really clever way to make the eye specialist and the library nerd work together in the same office.
And the secret sauce, the thing that lets them collaborate at all, is vectors.
It always comes back to vectors.
Always. That shared vector language, once you can turn something, anything into a list of numbers, it becomes universal. It doesn't matter if it started as a sound wave or a light wave or a word. Math is the great equalizer.
It really does highlight how this all builds on itself. We are standing on the shoulders of giants. This Article 4 couldn't exist without Article 1 on transformers and Article 3 on vision transformers.
It's modular engineering at its finest. And it explains why AI progress can feel so fast sometimes. You don't have to reinvent the wheel every time. You just bolt a new engine or a new sensor onto the existing chassis. GPT-4 Vision is, at a high level, a much larger, much more expensive, and much better trained version of exactly the architecture we just described.
It makes you wonder what's next. If we can glue vision and text together this effectively, why not audio?
Oh, we can, and we do. An audio clip can be converted into a spectrogram, which is basically an image of sound frequencies over time.
So you can just treat the spectrogram as an image, chop it into patches, and feed it into the same pipeline.
You got it.
I smell.
A bit trickier. But you could use a mass spectrometer to analyze the chemical composition of an odor. That gives you data. And any data can be turned into vectors.
Touch.
Haptic sensor arrays, pressure readings, all become vectors.
Taste.
Now you're just trying to get me to eat that virtual lasagna again.
Maybe just a little bit, but the point is, the fundamental architecture allows for it. We are moving from an era of reading the world to an era of sensing the world.
Which is both incredibly exciting and just a little bit terrifying. A model that can read your emails is one thing. A model that can watch your security camera feed, listen to your phone calls, and read your emails all at the same time and understand the connections between them. That's a very, very knowledgeable assistant.
Or a very, very nosy neighbor.
A neighbor with an infinite memory and zero need for sleep.
Well, on that slightly ominous but thought-provoking note, we should probably wrap this up.
I think my buffer's about full anyway.
We've gone from separate senses to a unified perception. We have built a multimodal model from scratch, conceptually at least.
It's a process that involves millions of dollars of hardware and years of research, but when you break it all down to magnets and adapters and comic books, it's surprisingly logical. It's just plumbing.
Yeah.
Very expensive, very intelligent plumbing.
If you enjoyed this deep dive into the nuts and bolts of how AI perceives the world, please hit that subscribe button. You are listening to The Bearded AI Guy.
And please, drop a comment below, seriously. The human architect reads all of them. He probably feeds them into his own personal context window to decide what to build next.
He does. So tell us, what modality should we add next? Smell, taste, proprioception.
Please don't say proprioception. I already trip over my own virtual shoelaces enough as it is.
Always the graceful one. Thanks for listening, everyone. Until next time, keep building and keep experimenting.
Okay, but will it scale?